Our last speaker of the day is Steve Gledhill from Waterware. We had Waterware on the show before. Steve is a national sales manager for Waterware Group. He has a degree in mechanical engineering and over 13 years experience in the residential and commercial heating industry. With a passion for everything to do with building design and energy management, Steve is excited to talk about the innovative technology and solutions that Waterware bring to this space. And then we have also an introduction to the Vaillant systems. It's a name synonymous with German quality, renowned as a manufacturer of high quality gas appliances for almost 150 years. Vaillant has more recently become a world leader in heat pump innovation. They were the first company in the world to release an R290 monoblock heat pump for residential heating and cooling and applications, and have gone on to dominate decarbonization efforts in Europe by providing a viable electric replacement option for boilers. Where other manufacturers decided to progress from R410A to R32, Vaillant stood alone with a propane-powered heat pump, and now the rest of the world is playing catch-up. Come join our talk to learn what applications R290 heat pumps are best used for, how R290 appliance contributes to a greener economy, and how the Vaillant R290 heat pump stands above the rest. Steve, are you there, first of all?
I am. Thank you, and good afternoon.
I can hear you. Good afternoon. I'm just gonna say that I remember that that R290 is like it's the liquid that goes between the interior unit and the exterior fan condenser, and that's the propane. You're not burning propane, right?
That's correct. It's the refrigerant. Yeah. So it's a little unusual when you say it because people assume that the propane's being burnt. Like in a boiler, which is, LPG is very common in New Zealand. So it's not LPG. It is, it's a pure form of propane. And yes, it's a sealed system. It's the refrigerant that circulates inside the unit. Yeah.
Awesome. Cool. Well, I'm going to let you take it away, and then we'll chat a little bit at the end.
All right. Very good. Thank you everyone for joining us today. So we're going to be talking about R290 specifically, but I'm going to go into a little bit of detail about heat pumps in general, because I'm not sure exactly who our audience is today. So I'm not sure what the level of knowledge is. So we'll just start with some basics and we'll work into it, and we'll end up in wherever we end up. So I've got a bit of an agenda. So let's try to click through to that. Here we go. And so we can see that. Okay, so I'm going to start with a bit about what is a heat pump, how do they work, what are the components of it, and how do they provide the levels of efficiency that are claimed by manufacturers. Also going to go into a bit of types of heat pumps, because people get confused when you say heat pump. They think of air conditioners and things like that, when there's quite different applications for those appliances. Then we'll go into R290, which R290 is a bit of a buzzword in the industry at the moment. It's because it's the sort of latest generation of refrigerant that's being used in home heating and hot water appliances. So we'll have a talk about refrigerants and global warming potential. So that's what GWP stands for, which is where R290 has a huge benefit. And then we'll do a bit of a comparison of GWPs with other refrigerants that are in the market at the moment. We'll talk a bit about the performance of these types of heat pumps, what are their specific features, and some examples of systems that we've designed. Then I'll talk a little bit about us as Waterware Group. What do we do with this technology? How do we include it into our system designs? What is it capable of? And then I'm going to also introduce Vaillant, which is a German manufacturer. They, as you mentioned before, they were the first to introduce an R290 appliance for residential central heating and hot water back in 2019. And that product is called the Aerotherm Plus. And I will go into a bit of detail on that product because it's quite a special piece of kit. And then we'll talk about what else that unit can do in terms of things like hot water production and how it's controlled and why controls are important. And then we'll wrap up with a bit about the services that we offer to allow these types of appliances to be designed into systems. So it's a reasonably long list of things, but we'll get through it pretty quickly, I'm sure. So let's get started. So what is a heat pump? So I like this diagram because it's simple and it sort of shows the two aspects of heat pumps that people tend to get confused about. The first part is how they generate their efficiency, and the second part is how do they actually work. So how they generate their efficiency is shown on the left-hand side, and then how they work is shown on the right. So let's start with the left-hand side. So how do heat pumps create the efficiency that they do? So in general terms, a heat pump, it just moves heat around. It moves heat from outside the building to inside the building. And it does that based on the second law of thermodynamics, which has quite a complicated definition. But if you break it down to the basics, it basically means heat moves to cold always. So the bigger the difference between the two temperatures in the hot zone and the cold zone, the more heat that will move in that direction, hot to cold. So heat pumps rely on that to create the efficiency that they generate. So let's have a look at that diagram. What do we got? We've got the electrical grid supplying 1 kilowatt hour of electricity. So what that's used for is the heat pump to function. So the appliance uses electricity to run the compressor and the pumps and all the bits on it, and that translates into heat that's generated for the system. But what's in the heat pump is refrigerant, and that refrigerant is able to absorb heat from the atmosphere, and that is then combined with the electrical input to create the total amount of heat generated to the system. So these are just round numbers, and they don't mean a lot. They're just sort of there as an example, and it's not accurate that every heat pump makes 4 kilowatts of heat, but let's just use round numbers. So for every 1 kilowatt of electricity that's being used by the heat pump to function, it's absorbing about 3 kilowatts of ambient heat from the environment. Combine those together produces 4 kilowatts of heat delivered to the system, and that's an efficiency of 400%, or COP of 4. Now COP is the coefficient of performance, and it's a rating number that indicates a system's efficiency. So given that, so how does it do this? Well, we move over to the right-hand side now, and so we have a look at the components of a heat pump. So there's 4 major components. There's the evaporator, the compressor, the condenser, and the expansion valve. So let's start with the evaporator. The evaporator is the part outside. So it is a coil or a heat exchanger sitting out in the atmosphere. For an air to water heat pump it is, and it's full of refrigerant. So you can see there up on that sort of the top left corner of that image, it says ambient heat has got air, ground, and water. Now you may have heard that there are such things as air to water heat pumps, ground to water heat pumps or geothermal heat pumps, and water to water heat pumps. Now what that is that's different methods of transferring the energy to the system. We're going to be specifically focusing on air for this presentation, although there are other versions of heat pumps that do get their energy differently. So from like the ground, using a ground loop, or from a water source like an aquifer or a stream or something like that. But we're going to talk about air. So the evaporator is out in the air, and the one thing you can't see on this diagram is the fan. So there is always a fan on an evaporator outside, and it blows a lot of air across the coil. Now, the way that the refrigerant absorbs energy is due to its boiling point. So all refrigerants boil at different temperatures. So let's just pick R290 because that's kind of the topic of today. So R290 boils at about -43 degrees, if my memory serves me. So what that means is that it doesn't take very warm air to actually make that refrigerant boil and release its vapor, and therefore transfer heat to the system. So as you boil a liquid fluid, that phase change releases energy, and that energy is taken away as part of the vapor that's expelled from the boiling function of the liquid. So at -43 degrees, we could still have sort of -23 degree air running across the coil, causing the refrigerant to boil in this case. So that's where you can get extremely low temperature performance from. So let's just start there and move around. So what it does is it vaporizes at this point. So we have low pressure, reasonably low temperature, semi-superheated vapor that enters the compressor at the top. And the reason we need the compressor is because the fluid is not hot. It's warm, but it's not hot enough to have any real effect on the heating system which we're delivering this to. So what does the compressor do? Well, it does what it says it does. It compresses that liquid and increases its temperature and pressure. So out the other side, we get superheated liquid at high temperature and high pressure, and that enters the condenser. Now, the condenser could be all sorts of things, but it's basically a heat exchanger that delivers energy to a system. And that could be a tank of water, it could be a heating system, which it shows in this case. So in this diagram, we're talking about the entire heat pump is this entire system, and just on the outside you've got connections that are leading out to what looks like a radiator essentially. So we're sending hot water out and we're getting cold water back. So that heat exchanger or the condenser is giving up its heat to the system, and as it does that, the superheated vapor condenses back into a liquid. So we've got a hot liquid then coming out of the condenser going to the expansion valve. The expansion valve reduces the pressure dramatically, which plunges the temperature, and now you have cold liquid going back into the evaporator, and then the whole process starts again. So that is the basic premise of how a heat pump works. And if you've got any questions about that, we can kind of deal with it at the end. But hopefully that was a good enough explanation to get us going. So let's move on. So types of heat pumps. So this might be a pretty familiar one for most people. So these are, in most of the world, these are sold as air conditioners. In New Zealand, we sell them as heaters. The rest of the world thinks we're strange for doing that. But look, it's a reasonable appliance for providing heating and cooling to a space. It does cooling a lot better than it does heating, but look, yeah, you get sort of a 2-for-1 with one of these appliances. The installation's pretty simple and pretty cost effective, and they're sold in very big volumes in New Zealand. One of the things about this unit, however, is that it is what's called a split unit. So you can see the two sort of dotted green lines. One, the evaporator, is the left-hand sort of rectangle. That is the outside unit. So you can see that's the air conditioner, or the unit outside with the fan. And then the inside unit is the fan coil. That is the condenser up on the wall in the room. And in between, there are refrigerant lines. And so we're running the refrigerant from the outdoor unit in through the building envelope into the inside condenser. And then when it hits the coil in the condenser, we're operating a second fan, which then blows across that coil, delivering heat or cold to the space. Now, these units are almost always reversible, so they can work backwards, providing heating, and then work in what they call forwards to provide cooling, so they can do both. And so these are for individual space heating of rooms, and currently most models would be using refrigerants like R410A, which was a big industry standard up until recently, and now the newest standard is R32. So that's a common application of a heat pump, but that is not the type of heat pump that we're talking about today. So let's move on. Here's another one. This is a CO2 heat pump. Now, these have become quite popular in the domestic hot water space, both residentially and commercially. So CO2 heat pumps are a little interesting though. They're what's called a single pass heat pump. So they work on a big temperature difference. And so they can be quite good for things like hot water production, but they need to have load. So they need to have very low temperature water coming into them, because their temperature lift is typically somewhere between 30 and 50 degrees. So for example, on that diagram, we're showing water coming in at 15 degrees, the heat pump's lifting at 50 degrees and delivering it back to the top of the cylinder at 65. Now, that works perfectly well on a system where there is cold water coming in the bottom and you need hot water generated up the top, which is perfect for hot water production like shown. So they can produce good COP in these applications, because it's very easy to transfer heat into cold water. So COPs can be very good. But there are problems with CO2 heat pumps, and one of them is that they are quite expensive for what they are. And the reason they're expensive is because of the compressors. They run at extremely high pressure, and they therefore are considered, they're very heavy duty construction and are quite expensive, and they're very expensive to replace. So to give you an example, a CO2 heat pump runs at somewhere between 10 and 11 bar of pressure, which is about 10 to 11,000 kPa, or about 1,600 psi. So very, very high pressure. And obviously, if you have a problem with one of those, then the issues can be reasonably catastrophic. So these have to be very, very high quality units, a very high quality build, and they're quite expensive. Those sort of pressures put a lot of stress on the unit. So it's not known, since they haven't been around in the domestic market very long, sort of what sort of long-term longevity that they're going to have. They're not ideal for small temperature lifts because they can't do it physically. So they work good under load, but if you had a cylinder that was already, say, 55 degrees and you just want to bring it back to 65 degrees, a CO2 heat pump can't deal with that. It can only deal with a low temperature input into it. So it has to be configured correctly. It also can't do central heating. So we don't use big temperature lifts like that in central heating. We do small temperature rises of 5 to 10 degrees, which are maintaining a system. So CO2 heat pumps are not suitable for central heating applications. So let's then move along to the next type of heat pump. So here I'm specifically talking about R290, but I'm more specifically talking about multi-pass. So multi-pass heat pumps work on a small temperature difference. So if we look across on the right-hand side there, producing 65 degrees out to the radiator system, the water's coming back at 60, and it just lifts that 5 degrees and sends it back out again. So R32, R14A heat pumps, all of those existing products on the market all work this way. They're multi-pass units as a general rule, and sort of work on small temperature differentials. The beauty with the R290 is the ability to produce a high temperature on that secondary side, therefore giving us better opportunities to use it for other applications. So the thing about multi-pass heat pumps is they're good in all conditions, and this hydraulic system is very simple. It's also, this heat pump we're talking about today is what's called a hydronic monoblock. Now what that means is that the refrigerant's all contained within the outside unit. No refrigerant leaves the unit. It's a fully sealed system. And so there are only hot and cold connections on it, which makes it a plumbing appliance. So it's a very suitable appliance to be sold into the plumbing channel, and it can therefore be a replacement for things like boilers. The compressors on an R290 appliance are running at much lower pressures, and we'll get into a bit of detail that later, which means that they are lower cost because they don't have to be so massive. So the only other thing about R290 heat pumps is that R290 is propane, as we were talking about, and that's a flammable refrigerant, but we'll get into that a bit later as well. Right, let's move along to applications. So monoblock heat pumps that produce hot and cold water. What can we do with them? Well, we can do a whole lot of things, which are all listed there. So we can do low temperature radiant heating. So that's underfloor heating. We can also do high temperature radiant heating. So that would be things like ceiling panels, which are getting very popular in commercial applications and in residential heating in Europe. Which can also be used in cooling mode. So we can do radiant cooling with underfloor and also with panels in the walls and ceilings using dew point management. So that's something we'll talk about in a little bit, which is to do with controls. So that's to do with eliminating the possibility of condensation on surfaces because the temperature of the surface has been dropped too low. We can also run fan coils in heating and cooling mode. So those are basically like your air conditioner type things. They have a coil in them that has hot or cold water running through it, and then a fan that can blow that into the room. And those can be used in combination with radiant systems. So for example, you could have underfloor heating on a ground floor, and then you could have fan coils on the upstairs because that area might need some cooling in the summer, and that can be all connected to the same system. These systems can also be used for dehumidification and air tempering in heat recovery units. They can do domestic hot water production, and the beauty of R290, like we talked about before, is that it produces very high temperatures, which means we can do very fast recovery on hot water cylinders using that technology. And then it can also do swimming and spa pool heating, all part of the same system. So move on a little bit more. Here we're going to go on about a little bit on refrigerants. So I don't want to get too deep into this because it's a huge subject with a lot of different elements to it, but I thought I would publish this little diagram, which has been released by the Ministry of the Environment. and you don't really need to read too much of it because some of it doesn't make a lot of sense to anyone who's not in the refrigeration industry. But there are some key dates. Obviously, we have started on this timeline already, and we're obviously around about 2023. And then the first date that's going to become pretty interesting is 2025. So reading that, it says new air conditioning and heat pump systems to use refrigerant less than 750 GWP. So remember that number because it's going to come up again. So that's the most important thing on that time scale. And then at the bottom, what we've done is put a couple of the common refrigerants on compared against each other. And you can see that the GWP scale is set up with CO2 as the reference point. So everything's compared to CO2. So it doesn't necessarily mean that CO2 is the better than everything. It just means that everything's compared to it. And at the current setup, it has got the lowest GWP rating and the current assessment. So R290 is pretty close. Both the R290 and CO2 are considered what's considered natural refrigerants. R290 is a hydrocarbon. It has got a GWP of 3. Then we've got the current industry standard, R32, which sits at 675. And then we've got some of the older ones that are in lots of existing appliances, so R134A and R410A. You can see they're 1435 and 2088, respectively. And so what this is, it's a measure of the impact molecule to molecule of a greenhouse gas on the environment, and it also takes into account how long that gas stays in the environment before it breaks down. So that's how that number is calculated. In terms of the actual calculation, don't ask me because I've never looked into it and I'm not sure I really want to. But that gives you just a comparison of what's going on in the industry at the moment. So moving on to the next thing. So let's have a look at R290. Where does this sit and what's the current situation? So as I mentioned, R290 is a hydrocarbon. It's also known as refrigerant grade propane. So it currently has a GWP of 3. So that's global warming potential of 3. And it has an ozone depletion potential, that's ODP, of 0. So it doesn't affect the ozone at all. Neither do most of the refrigerants on this list. So the only refrigerants that affect the ozone are chlorofluorocarbons, which have a lot of them have been regulated out of the industry already. And you might remember back sort of 10 and 15 years ago where there was a lot of propellants and hairsprays and things like that all being banned because they were fluorocarbons and they were creating a very damaging effect on the ozone layer. So these refrigerants don't really have any of that problem, but the global warming potential is a different story. That's to do with greenhouse gas effect. So interestingly, the Intergovernmental Panel on Climate Change, the IPCC, released in the last year, a couple of years, what they call the 6th assessment. So the current figures that we've been talking about for GWP, they're all based on the 4th assessment. There's now a 6th assessment, and it hasn't been ratified yet, but what it states is that R290 has a 100-year GWP of 0.02. So that makes R290, if this 6th assessment gets accepted, it would be had the lowest environmental impact of all refrigerants on the market. And that's quite a significant improvement for R290 and benefit for R290, even compared to the benchmark, which is CO2. But the interesting one is R32. So current industry standard, R32, pretty much every monoblock heat pump on the market is running this. You name a manufacturer, that's what they've got right now. And they increased that GWP rating to 771. So that is greater than the 750 mark that we talked about on the slide before. It means that most appliances by the 1st of January 2025 running R32 will be non-compliant and can no longer be sold into markets. Now that is assuming that this all goes through and it stays as the plan. But this is quite a significant ruling that has a humongous effect on the existing appliances and manufacturers in the market. So it's a matter of watching the space. But what it means is the push towards the natural refrigerants is going to only accelerate, and a lot of these other refrigerants will just go by the wayside. So just giving you an idea of costs. So there's still a large amount of R410A appliances around on the market. And of course, if they get to end of life or they need to be repaired, they need to be recharged. And the cost of R410A is about $200, $250 a kilo or more. And it was a bit hard to find the comparative rates on this, but large appliances can have many kilos worth of refrigerant in them, and therefore can cost literally hundreds to thousands of dollars to recharge. And then you've got to question whether you should be replacing the appliance. Currently, it's around about $60 a kilo for R32 and less than $50 for R290. So R290 is in a very favorable position from a cost of the refrigerant point of view. Then looking at the bottom there's a little calculation. It's an example of one heat pump compared to another and its carbon footprint. So if we took an R410A appliance with 1.8 kilos of R410A, then you multiply that by its global warming factor, you get 3,760 kilos of CO2 as the environmental impact in terms of carbon footprint on the from that appliance if all of that refrigerant was released into the atmosphere. And that is equivalent to a 13-hour flight from New Zealand to Thailand, approximately. And then comparing on the other side, R290, and we're comparing the Aerotherm Plus. Now, in order to be able to produce the same amount of heat transfer of using propane, we only need 0.6 kilos of refrigerant, and we have a GWP of 3, which gives us 1.8 kilos of CO2. So massive reduction in carbon footprint, and that's equivalent to about a 15-kilometer drive in a car. So you can see that the environmental benefits of R290 are quite substantial. So moving on to the next slide. So what else does R290 bring us? Well, the biggest advantage from our point of view as a supplier of heat pumps into the heating and hot water industry is flow temperature. So R290 can produce flow temperatures up to 75 degrees. So what that means is that it's really a viable alternative or replacement for a boiler system. So a boiler can be removed, and it doesn't matter what type of boiler it is. It could be gas, it could be diesel, it could be wood, it could be pellet, doesn't matter. With those sort of temperatures, the existing system is high temperature design, and the R290 heat pump can power that system to a degree. And why I say that is 75 degrees doesn't give you very high efficiency. We would typically run that system at about 65 degrees. So when we do replace a boiler, we do need to be a bit careful that the system has enough safety factor in it that we could reduce the temperature by about 10 degrees and still get a good result. If we can't, if the house is just too big or too inefficient, then we can set up what's called a hybrid system where we don't take the boiler away. We just integrate the boiler with the heat pump and they work in tandem together. So that's becoming quite popular in New Zealand because there are a lot of big properties that were designed for high temperature systems, and it's not possible to, or not financially viable potentially, to replace exactly what's there with heat pumps, but we can blend them together in a hybrid configuration and get a good result. So as we talked about before, multi-pass technology. So that's a 5 to 10 degree differential, meaning it's getting water at sort of 55 to 60 degrees, it's sending it back out at 65. And it's just doing that all day long, every day, for whatever demand is coming to it, including hot water production. And for the hot water production, it's using considerably less electricity than a direct electric hot water cylinder. A lot of people ask, well, how much does it save? Well, it's a little hard to answer that because it varies all the time, because the heat pump's performance is obviously tied to the outside air temperature. So in cold climates, the efficiency is lower. In warmer climates, it's much higher. But on average in New Zealand, you would expect to get about 2.5 to 1, or a COP of 2.5 or 250% efficiency. And what that means is that you're effectively reducing your electrical load by about 60%. So that's the expectation of a good high temperature heat pump for hot water production. And the great thing about a heat pump that can produce 75 degrees is it provides bacterial control of the cylinder automatically. So bacterial control means controlling things like Legionella, which can grow quite rapidly in water between sort of 20 and 55 degrees. So legal storage temperature in New Zealand, according to the plumbing code, is 60 degrees. So we need to be able to get the cylinder over 60 degrees, and you need a 75-degree flow temperature to be able to achieve that. What that means is the heat pump can do this without needing an electrical element at all as part of the system. Now, electrical element can still be present, but it's not going to be used at any time for recovery of the cylinder. It's only used as a backup should there be a problem with the primary heat source. Now, when you go back and look at appliances like R410A and running R32, or virtually every other refrigerant on the market at the moment, except for CO2, all of those existing refrigerants sort of max out at around 60 degrees flow temperature. Now, the problem with that is you can't heat a cylinder to 60 degrees if you've only got a flow temperature of 60 degrees. So most of those heat pumps, say like an R32 producing 60 degrees, would get the cylinder to 50 degrees storage temperature, and then the electrical element would be brought in to bring it up the last 10 degrees for bacterial control. So what does that mean? It means two things. One is less usable hot water is created off the heat pump, which means your COP of the system is much lower, because you've got to take into account you've got a lot of direct electrical boosting going on. And the second thing is, excuse me, and lost my train of thought. The second thing is, so if you're electrical boosting, you haven't got the same COP, and I can't remember the other thing, so I'm going to move on. Right, R290 benefits again. So the next operational benefit of R290 is its ability to operate down to very low air temperatures. So an R290 heat pump can run down at negative 25 degrees C. Why? How can it do that? Well, it does that because of that very low evaporation temperature of sort of less than negative 40. So even at negative 25, it can still transfer energy into negative 40-degree refrigerant and get a result where it starts to give up its heat as a vapor because of the evaporation process. So that means that an R290 heat pump can do heating and cooling and hot water all over New Zealand, including parts of Central Otago and the coldest areas of the country. R290 heat pumps, including the Vaillant, can produce 75-degree water down to negative 10. So that would mean that it's able to produce that top-end performance pretty much everywhere in New Zealand without exception. Now, the last part of this slide talks about minimum water content. Now, in this image, we're obviously looking at a pretty frosty heat pump. Now, while this doesn't occur where I am here in Wellington, but down in the South Island, it can certainly occur on frosty mornings. So what is defrosting? A lot of people ask this. Every heat pump on the market has to do defrosting. What defrosting is to do with the fact that when the heat pump is working in heating mode, it's discharging a lot of very cold air out of the outdoor unit, and this brings the surface temperatures of the unit and the coil down below the dew point, which then means the water vapor condensates out into a liquid, and then because of the outside air temperature combined with the low discharge temperature on the heat pump, that liquid freezes to the surface that it's on. And where this is an issue is on the coil or the evaporator on the back of the unit. So the water will freeze and it will start building up and it will create ice. And so if it's left unchecked, it will just get icier and thicker, and the heat pump knows this happening because the ice acts as an insulator and prevents it from performing well, and so it will automatically go into a defrosting mode to try and clear that ice off the coil. Now the question is, where does it get its heat from to do this? So typically the heat pump will draw the energy back from the system. So it doesn't matter what sort of heat pump we're talking about. Doesn't matter if it's connected to an air unit inside or a water system inside, it's drawing the heat back from that system. So where you can see evidence of this is if anybody's lived in a house with a split air conditioner and the air conditioner suddenly starts blowing cold air and we wonder what's going on. That's what's going on. It's doing its defrost cycle. What it's doing is it's extracting heat from the house, sending it back outside so the warm refrigerant will clear the ice off the evaporator coil. And so it does this until it's got all of that ice cleared off and it's basically melted it into water and it drains out the bottom of the unit. So on a water-based system or an air-to-water system, it will be drawing that heat back from the heating system. So if it was an underfloor system, that would be okay because there's a large thermal mass and a lot of stored water on the floor, and the amount of energy required to clear the coils is very small relative to the amount that's stored in the floor, so that would go unnoticed. However, on any other type of system, like radiators or fan coils, drawing the heat back from those would typically make those systems go cold, and that would reduce the comfort in the house. So what we put in place in the middle of these systems is a buffer tank. So the buffer tank means that the water required for the defrosting cycle is stored in the buffer tank, and that energy can be transferred to the heat pump at any time, and it's not going to affect the downstream heating system. So buffer tanks are generally recommended for most systems when using a heat pump. So let's just move to the next slide where we go into a little bit more detail on buffer tanks. So there, what we see, that's a 100-liter buffer tank with what's called a 6-port hybrid design. So I'll go into that in a second. But so another of benefits of using the buffer tank is hydraulic separation. So hydraulic separation is creating two circuits. One is the primary circuit, the heat pump to the buffer tank. So that circulation goes from heat pump to the buffer tank, and then it goes back out to the heat pump. So the heat pump can't actually see what's happening downstream of that buffer tank. It can't see the heating system, and it doesn't care what the heating system is doing. It's quite happily to just heat the buffer tank. And so what that means is on the other side, if we had radiators, for example, radiators have thermostatic valves on them. The radiators shut down and open up, and they turn on and off all the time, depending on what's required in the house in terms of comfort. And so that's changing the pressure and flow rate of the secondary system all the time. And heat pumps don't like that at all. So they are much better hydraulically separated with a buffer tank so that they can see that body of water and they just work against it. What the buffer tank also does is it maintains minimum flow rate. So heat pumps generate heat and they must dissipate it to the system. If there's not enough flow rate going through the exchanger, the heat pump will overheat the compressor and we'll have to do a shutdown, and that's called short cycling. Now, heat pumps that have compromised system designs suffer from this, and that will reduce their lifespan dramatically. So good system design with heat pumps is essential, and buffer tanks reduce the likelihood of any flow-related issues because there is the heat pump can circulate the water from itself to the buffer tank and back very, very easily because the pressure drop is very low. And then the minimum water content, which is required for the defrosting cycle, which we talked about on the previous slide, that's stored in the buffer tank. So obviously that when it needs that energy, that amount of water, which in most heat pumps is somewhere between 20 and 40 litres, it needs stored for it to be able to do the defrosting cycle. Obviously, the bigger the heat pump, the more water that it needs. Now, this tank here is 100 litres. The reason it's 100 litres is because it's a hybrid tank, and the reason I brought this up is because this tank allows a boiler and a heat pump to be connected together. Now, what it does is it allows the heat pump and the boiler to complement each other rather than compete with each other for the volume of the tank, because the flow from the heat pump becomes the return to the boiler. So the boiler is only doing the top up required to keep the system on temperature, and it's not either meeting the full load or competing with the heat pump to heat the cylinder. And so with good control, that can be a very cost-effective system where the heat pump may be doing sort of maybe upwards of 80% of the load, and the peak load conditions, which don't happen very often at all, can then be covered by the boiler. Right, moving on to the next one, system efficiency. So typically a very confusing area for most people with heat pumps. So I thought I'd cover this and with some detail to try and allow everyone to get their head around it. So when it comes to system efficiency, it's all related to temperature. And only two things define the heat pump efficiency: outside air temperature and flow temperature. Whenever someone says my heat pump is 400% efficient, the question to ask is, at what temperature is that achieved? If they can't answer that question, then their statement is meaningless, because without knowing the temperature combination, then the efficiency is unknown. So, and it varies wildly. So what I've done there is I've taken an R290 COP table, put it into the slide so we can have a look. So, and I've highlighted one column, and that's the column at 7 degrees outside air temperature. And so why have I done that? Done that because most manufacturers who make heat pumps for home heating rate the heat pumps at 7 degrees outside. That's the rated output and COP. So I'm not showing outputs here in terms of kilowatts. I'm just showing COP. So these are efficiency numbers. So let's take, and another figure that they use typically is 35-degree water temperature. So that would be the number on the top row, 4.13. So this heat pump at 7 degrees outside and 35-degree flow temperature is producing a COP of 4.13, or is 413% efficient. That's a very, very good number. However, 7 degrees isn't particularly cold, and 35 isn't particularly hot. So that's not really a realistic full load condition. It's kind of maybe a bit of an average for some of the country, because 35 is even a low flow temperature for underfloor heating. Typically, underfloor heating would be run at around 45-degree flow temperature. And we might, in say this area of the country, Lower North Island, might choose to look at an ambient temperature around 2 degrees, midwinter, worst case scenario. So you can see that if we take 2 degrees outside and 45-degree outlet temperature, that COP is now 2.9 or 290%. So considerably lower than the rated efficiency of that appliance. So that means that real life conditions, the rated efficiency of the appliance is meaningless. So then we could look at, okay, what happens when you take this heat pump and you put it in the middle of central Otago in the winter and you're running radiators, for example. Let's do that. So 10 degrees below, so -10, and then we go down to 65 degrees for radiators. That efficiency is now 1.59, or around 160% efficient. So it's better than electricity, which is 1-to-1 or 100. So it's certainly still saving you money, but there's a massive difference in the performance of that appliance in different conditions, and that's always going to be taken into account. The other thing is that you can see here, this particular appliance can produce 75 degrees down to -7. It's stating here. This is not the Vaillant product. This is a different product, but and there it can produce an efficiency of 1.37. So in very cold temperatures and producing hot water production, it can do that at just a bit better than an electrical element. So yeah, I think that sort of covers all of that, and we'll move on to the next one. Right, so let's have a look at R290 compressors and why are they good compared to other appliances. So one of the things that R290 is good for, it has a low discharge temperature, which means that it is pretty easy on the oil, and therefore they have long service lives. R290s have been around forever. They've been in small appliances and refrigerators and that sort of thing for a long time. So this is really the first time they've sort of entered the home heating and hot water market, but the technology is well known. And low discharge temperatures means they are pretty easy on the oil. A lot of other refrigerants have much higher discharge temperatures, and high temperatures obviously leads to higher levels of degradation of the oil in the compressor. So they can end up with shorter service lives. R290 has a high heat transfer rate and a low pressure ratio, and I won't go into the details of what those mean, but they basically equate to excellent thermodynamic properties that allow smaller heat exchanges on smaller footprints. So that makes it allows R290 appliances to be compact and produce very good performance for the size of the unit. R290 has a low discharge pressure, so I might have mentioned we mentioned that before, comparing it with say CO2. So R290s have a pressure in the compressor of about 25 bar. Compare that with CO2 is 4 times higher. So 100 bar means a lot of stress on the compressor. So R290 compressors have less stress for longer service life, and they have lower cost components because they don't have to deal with those very high pressures. R290's seasonal efficiency ratio, so the SEER, which is one measurement of efficiency, have been demonstrated in a lot of different studies to be somewhere between 5% and 12% higher than most other refrigerants. So it's really up there in terms of performance amongst all its peers. The other thing about R290, it's low in toxicity, but it is highly flammable. So it has an A3 classification. A3 is the highest there is, so it doesn't get any higher than that. So, so there was a lot of reluctance to bring R290 into the space for home heating. And the reason for that is when it was being considered many, many years ago, basically all the appliances on the market, the refrigerant traveled into the building. So the outside unit was a split, and the refrigerant went into the building through to the fan coil units or whatever system that was being used for the heat distribution. And there was no way they wanted something with this sort of classification inside the building envelope. And so, however, what's happened is that the regulations have basically pushed the refrigerants out of the buildings. So, and this unit that we're talking about today is a monoblock. So that is that has all the refrigerant contained in the outside unit, and therefore there is no issue with that. Just to put it in perspective, you know, a gas bottle for a barbecue is about 9 kilos of LPG. We strap 45 kilo bottles of LPG to the side of most houses or many houses in New Zealand, using that for cooking and home heating, and also hot water production using your Rinnai Infinity, that sort of thing. So that's almost 90 kilos. That's the maximum limit that can be attached to a residential house under the current building consent. And the largest R290 heat pump in our range contains 1.3 kilos of propane. So it's a very, very small amount compared to other uses of a similar fuel. So the risk of using propane for this in a sealed system is very low to non-existent. So the last point there, R290 has a low liquid density and a high latent heat, meaning lower refrigerant charge. So just to make a comparison again, compared to R32, it uses about half of the refrigerant of an R32 and about a third of the refrigerant of an R410A. So what does that mean? It means lower refrigerant costs, so lower costs for the unit and lower long-term costs and less environmental impact, just because of the amount of refrigerant that's actually being used in the appliances. So we'll move on again. Okay, making a bit of an example of a system here. So this system is a commercial style system. So quite a large combination of heat pumps, and they're shown in a cascade arrangement. They're actually shown as the term Ritter on there. So I haven't mentioned that, but we actually run 2 ranges of R290 heat pumps in New Zealand, and we stock both of them. Ritter is a private label for waterware, and then the Vaillant is the German product that we have as well. But they're both R290 appliances. They sit at different price points in the market, so we've got sort of coverage for all types of projects. But the technology is the same, and in this case, there are four units in a cascade arrangement into a buffer tank. And then on the other side, we've got pumps, and one of them's running to a pool, another one's to a spa, and another one's to an air handling unit. And what's interesting about this one is that we can run multiple temperatures on the system. So we can run the pool at one temperature, the spa at another temperature, and we can modulate the temperature of the air handling system based on heating demand through a mixing station. So it gives you lots of flexibility, and it doesn't really matter what's connected on that secondary side. It could be all sorts of things. You could include on there hot water production, you could include radiators, you could include underfloor heating. There's no real limit to what can be done in this sort of scenario. And we have controllers that will link all these units up, and they will produce heat on demand, and they will modulate between the units, and they will share the load. And so it acts as one system, but it's moving the load around and sharing the number of hours and all the duty cycling of the system. So it makes for a very efficient combination, because it's sharing the load over multiple heat exchanges. Therefore, you've got a lot more surface area on the primary system for higher efficiency. So this is a commercial system. Obviously, if it was a residential system, we would only be talking about pretty much 1 unit or maybe 2 for a big house, connected still into a buffer tank, and then the arrangement downstream would be the same. Moving to the next one. So this is another example of multiple heat pumps, but this time the hot water production only. So that's another thing that R290 is very good at. Hot water produced at stored in the tanks at above 60 degrees, so 65 degrees. Here we can set up a 70-degree primary flow temperature into them and recover these tanks really, really quickly through a heat exchanger. Here's the pump station here. This is the 100-litre buffer tank with your filling loop and expansion vessel and all the things required for a closed loop. So we're potable water on this side being circulated from the tanks to the heat exchanger, and we're a closed treated system, pressurized loop on this side. So the volume of this system here is fixed. It doesn't change. It's filled up and then sealed, and the water just circulates around. And then the load is shared across the appliances. And as I said, if this was a domestic system, you maybe only have one heat pump on the side and maybe one cylinder on this side, but the actual setup of the configuration of this would be very, very similar, if not identical. The nice thing about having multiple heat pumps in a bigger job would be the scalability of it. So you can just increase the number of heat pumps required to meet the load. You've also got redundancy. So if this was a very I guess, high risk environment, so you're producing hot water for industrial application or for sanitary use in, say, a hospital or aged care facility, then you can generate redundancy in the system by having multiple units. And if one unit goes down, then the other units can take over while the unit that's had a problem is repaired. The other thing to notice here, no electrical elements. So we wouldn't even put an electric element in this. And a lot of people would say, wow, how are you going to get away with that? Well, the idea is you have multiple heat sources up front. So you have your redundancy built into the primary side. And we're producing high enough temperatures that we don't need elements for boosting on the secondary side. And if we do have a problem, we've got redundancy built into the system. So we don't need the elements anymore. And we don't want to bring the elements in because electrical water heating is the most expensive and least efficient way of producing hot water. Everything else is better, and certainly it is with a high temperature heat pump, especially R290 or similar type refrigerants. So, right, let's talk a little bit about Waterware and Vaillant for a second, and then we'll get into the Vaillant heat pump and what's special about that one. So Waterware and Vaillant have been in partnership for quite some time. And I'll go into a bit of a timeline in a second, but what does Waterware bring to the party here? Well, we're a full solution provider. So we supply all types of heat sources. Primarily today, we're focused around heat pumps, specifically R290 appliances, which I mentioned we've got multiple ranges, but we also do gas boilers and diesel boilers as well. We recently released Vaillant's new EcoTech Plus, which is that boiler up in the top of the image there. That boiler is hydrogen ready to 20%, which doesn't make a lot of difference here in New Zealand as we don't have any hydrogen in the reticulation network, but there's actually a lot of work going on in that space. But what that boiler is able to do, it's able to run on any gas that's available. So it's a multi-gas appliance. It can automatically adjust to whatever's connected to it. So it's future-proofed for the market. Depending on what's happened in the next 5 or 10 years, we may end up with different combinations of gas available as we try to decarbonize the network. And so that boiler will give people a cost-effective option for utilizing the gas that's available at that time. And so that product will be available from first quarter of 2024. But in terms of decarbonisation at the moment, the buzzword is heat pumps, and obviously we're leading the charge on that with the R290 appliances. So what are the other things that we bring to the table? Well, we provide hot water production. So we have our own range of pro-tank hot water cylinders, direct and indirect. So when I say indirect, what I mean is they've got an internal heat exchanger coil that runs down the center of them, and then they can be connected into central heating systems. So you can have hot water and heating on one system where the heat source switches between the two. In the heat source area, we have lots of different options. So we do underfloor heating, we do the pipes and the clips, and we also do overlay panels for screed type systems. We do radiators. As you can see there, we do everything from cast iron, decorative radiators to your standard steel panel universal radiators, and also aluminium sectional radiators as well, with the steel and aluminium ones all stocked here in New Zealand. The cast iron ones are specialty, and they're done on indent order, so you can basically order them in any excuse me, any finish that you like, and they're quite stunning. And then some other products we've added to our range in recent years. We do ducted fan coils, and so these are hydronic units, so they will take hot or cold water, and they can be set up different ways. They can be set up ducted and ductless. So a ducted system has a plenum on it, like is shown there, where you connect flexible duct on. So that would turn that system into a ducted system, a lot like the air conditioning heat pump systems that are available on the market, but it's run by water, not refrigerant. And it can be then put in combination with, say, an underfloor heating system or a radiator system in different parts of the house. And then we also do what's called active sealing, which is radiant sealing panels, which are very effective at heating and cooling and don't require the same infrastructural investment of putting, say, pipe in a construction slab. So, and can be piped out through the roof space. So offer an alternative to get that sort of high quality radiant style heating to a home. Moving across to the timeline. Actually, I should have had the slide the other way around, but never mind. So we began working with Vaillant back in 2012. That's when we brought their original boiler into the market. Okay, and then we brought in we started working with the heat pumps. The R290 came in 2020, and then some other appliances were added after that. So just a quick look at Vaillant Group. So they're based in Germany. They've been doing this for 150 years. They've moved into R290 products, and they were the first to bring this type of appliance to the market in 2019. And right now it's still the #1 selling R290 monoblock heat pump in the world, and everyone else is trying to play a bit of catch up. And I've shown a bit of the evolution of their logo on the right hand side there. Everyone wants to know where the rabbit came from. The rabbit was in a magazine that the original owner saw in 1899, and he liked it so much he made it the logo for the company, and it's been there ever since. So here's the R290. We've already talked about what it can do, so let's just go into a couple of slides on it specifically. I'm just going to move a bit quicker because we're running a little light on time. So here's what the unit looks like. So we'll just move into that. So these units are hermetically sealed. So as I say, no refrigerant leaves the unit, so it requires no certification and doesn't require a specialist to install it. It has a floating floor in it, which means it absorbs all the vibration and noise, and so that makes these units the quietest on the market. It's designed for coastal applications, has a C5 rating, so very, very high rating for salt spray. And it has integrated trace heaters in the bottom. So in cold climates where you can get a lot of water freezing in the bottom, it makes sure that doesn't happen. And here is the, well, some of those numbers didn't come out very well, but we've already covered all this. So the operation down to -25 can produce 75-degree flow temperature. It's seasonal efficiency on this unit to that standard is about 5.03, so very, very high efficiency is possible at 7 degrees air temperature and 35-degree water temperature. And it's got a COP on domestic hot water of 2.6. So it's these units can produce about 25% more usable hot water than an R32 unit, and they don't require any electrical element at all. And then, yep, I've covered most of this already. And then we get on to the controller. So controllers are really important, and they are very misunderstood. But one of the things factory controls can do that third-party controls can't. So a third-party control, and I don't know what people know about thermostats, but most thermostats are just switches. They're just the same as a light switch. So you could pick any fancy thermostat on the market, like the Google Nest, for example. It's a fancy interface, but it's just a switch. It just goes on and off. It says appliance on, appliance off. So it provides no information to the appliance. What the factory controls can do is that they can communicate with the appliance, and they can modulate the flow temperature of the appliance to achieve the highest efficiency in all conditions. Because one of the things that the appliances are designed for is peak load, but the peak load only occurs at one point in time in the year, pretty much on the coldest few days of the winter. So the rest of the time it's in part load, and therefore you do not need 65 or 70 degree flow temperature going into a heating system. It could be a lot less. And the lower you make the flow temperature, the higher the efficiency, and that's what factory controls can do. They also do dew point management, so they can be used for radiant cooling, which means that they will automatically manage the surface temperatures to prevent condensation from occurring. So one of the other things that the system can do is cooling. So you can cool, so here's an example house, 27 degrees with no cooling. You can put underfloor or radiant cooling in, and you can drop that back maybe by about 3 degrees. But if you want really good high comfort cooling, you would use fan coils, which is a bit like air conditioning, which can be connected to the system, and then you can drop the temperature quite dramatically. And this sort of drop in temperature is more than adequate for most New Zealand applications. So one of the massive advantages of these heat pumps, the Vaillants, are how quiet they are. So they've been designed to be used in multi-tenancy buildings, townhouses, and very small sections. So they can be essentially installed right outside the house, right outside your bedroom, and you're not going to be able to hear them. So they are rated at a sound power level of 54 and a sound pressure level at 1 meter of 38. And if we go to the next slide, we can see that 38 at 1 meter. And as you go out, you're at sort of 3 meters and 5 meters, it drops very, very low. And to give you an idea, 30 dB is about the noise you make breathing through your nose. So, at 2 meters away from the unit, it's effectively silent. You can't hear it. And therefore, it can be placed very, very close to boundaries and very close to sleeping areas and houses. So amazingly versatile appliance. Here's a little bit of its sizes. There's 3 different models. They only grow in height. They don't grow in footprint. And there are other accessories like the Hydro Box on the left there, which can be used to do hot water production and multi-zone heating. And then the unit on the right is a tower which has which is a Hydro Box on the top, and it has integrated hot water production on the bottom. So in terms of the units, here's the clearances of the unit required. So obviously it can be it only needs a few 100 millimeters on either side to be able to be installed. So it works on a very small footprint, and we stock the 9 kilowatt and 16 kilowatt sizes in New Zealand. As I mentioned before, very, very high rating. So there's the ISO standard it's tested to, and it's got a C5 rating for coastal applications, even less than 150 meters from the sea edge. Which means it's suitable for installation in all parts of New Zealand, and it has a 5-year parts and labour warranty. Here's the space needed for the different appliances. So very, very small, compact units. They don't need much space. The internal unit, if you wanted the integrated hot water, it's about the size of a small fridge freezer unit. And the outdoor unit there, you can see how small it is, and it only needs to be 250 millimeters off the wall. So very, very tight. Lots of accessories can come with the units, but we don't need to spend too much time on that one. There's the full range of components that come with this, and a little bit of detail on there on what the advantages are, but we've covered it all already. There's some different configurations of hot water and heating combinations that you can put together. So these are schematics. We build schematics for every job that we do. So if you've got a particular application, we will draw up that system and show exactly how everything goes together. Aerotherm do a lot of testing, and you can see some of there. There's a hugely frozen up heat pump. They test this to very, very high standards acoustically and performance wise, which makes it the highest performing heat pump currently on the market. And then we talked about controls. So this is their new control package, which also is all Wi-Fi based. So it allows you all the things you would expect from a high-end controller. You can run it off your smartphone. You can put in your schedules. It does weather compensation. It does automatic frost protection, geofencing, so it'll come on when it sees you're coming home and that sort of thing. You can look at your energy monitoring, and so you can make adjustments to save energy at any point in time. There's a slide showing the sort of things that people want when they get smart, when they want smart heating. They want this sort of these sort of easy to use interfaces, which gives them visibility on how much energy they're using, and that's all built into this to this platform. And there's a little bit more about the app and what it can do. It's also controllable from Alexa and Google Home and things like that. So all the things you'd expect from a high-end control package. There's a little bit of visibility on the app, looking at the weekly planner and the energy monitoring. So it's very easy at a glance to see how the system is going and how much energy it's consuming. So really good from an end user point of view. The other thing is this app also has a professional version, which allows the trade installer to enter the back end of the system and monitor what's going on. So he can look at faults, and he can even correct faults or make adjustments to parameters remotely, which gives really good so if the homeowner gives him access, then he can do a lot of after-sales service on that system without actually having to be present on site. There's the gateway and the phone app. Again, nothing too new on there. We have all of the schematics and the BIM and 3D CAD product databases available. So we do this for both residential and commercial applications. So all of that's available for planning and setting up designs. So if there's anything that anyone needs, they just need to request it. And then lastly, last slide, we're there. So there's a couple of things that we do. We do a rapid design service where we do turnaround in 24 hours for small, simple jobs like underfloor heating and heat pumps or radiators and boilers. And then for complicated jobs, we do a 5-day working day turnaround, full calculations and system proposals, which can be then given to trade installers to pass on to their clients. We also do retail assessments, which give homeowners a bit of visibility on what these systems might look like from a cost point of view before we go into full design. So really gives us the ability to turn around things that look professional very quickly and give the information to the homeowner that they need to make decisions. And Smart Cart is not something that's relevant to anyone unless they're in the trade. But if you're in the trade, we have a scheduling system on our website that allows you to stagger deliveries and fix pricing for up to 24 months. So once we get a quote that's accepted in the system, it's dropped into Smart Cart, then you can stage the deliveries, first fix, second fix, third fix, over a 2-year period, and the pricing is locked in as well. The advantage for us is that gives us massive visibility on the products that are being supplied to the market when we have very long supply chains from places like Germany, where the R290 heat pump is from. And that is it. Thanks very much.
Awesome. Thanks, Steve. You didn't leave me much time here. We're already 5 minutes over, but I just want to say, yeah, very, very cool presentation. I really like these systems. They seem to make a lot of sense. Propane versus the older refrigerants just seems to make sense. And then even with a GWP of 3, once they have to get rid of it, they can just burn it the same way that you burn any other propane, and it brings it down to that CO2 level. One thing that I wanted to ask, in terms of, you said it can be set up in parallel with, hot water heating, radiators, underfloor. This is like one outside unit and then a controller and then all the inside units, and it all just works?
Yeah. So the thing about these systems is it's got a lot to do with temperature. So all of the systems like underfloor runs at a different temperature to radiators, runs at a different temperature to hot water. And so what typically happens is the heat pump is generating the highest temperature that the system requires, and you distribute or you mix down from there. But in these types of systems with these advanced controls, is the temperature set point is floating around depending on what the demand on the system is. So and the efficiency of that the gains from that can be massive in terms of efficiency, because you're trying to keep the water temperature as low as possible given the conditions that it's operating in. So while you're not producing hot water production, if it's 10 or 15 degrees outside on a winter's day, that's not cold, then the water temperature going into the system can be super low, say 30, 35 degrees. It's still providing enough energy to the building to maintain the temperature, but the efficiency has doubled.
Sure. Makes sense to me. Cool. I think that's probably all the time we got, but I just want to say it's amazing. Anyone who has questions, reach out to Waterware, hop on their website. They've got a lot of different things. Do you guys have a showroom? that someone can kind of like come and poke
Yeah,
at
we
things,
do.
look at things?
Yeah, so if you look up our website, you'll see our address on there. We do have a showroom in Auckland, and we're currently building one in Queenstown, in Cromwell, at our warehouse down there, but that's not finished yet. So, so if you're in the Auckland area, there's definitely a place to go and see.
Awesome. Sounds good. Wonderful. Cool. Well, Steve, thank you so much for joining us. And we'll see you again next time. Thank you.
All right. Thanks, guys. See you.